Hi, welcome to another video in my series on the applications of Demoivres' theorem. Now, what we've got in this example is how we can go about expressing the cosine of a multiple angle, in this case 4 theta, in terms of cosine theta, or cos theta for short. And we do this by using the theorem. This part here in the bottom, we know that cos n theta plus I sine theta is equal to z to the power n, where z is equal to cos theta plus I sine theta. And we can take this part, cos n theta, the real part, and compare the real coefficients. I'll show you how, okay? What we do is, for an example like this, we write down the cosine of what we're given, in this case 4 theta, and then write plus I sine 4 theta. Now this is going to be identical through Demoivres' theorem as cos theta plus I sine theta all to the power 4. Okay? Now we're going to expand this in a moment, but because it's quite lengthy, what I'm going to do is rewrite this as just simply c plus is all to the power 4. It's up to you whether you do that, but it certainly pays, in my opinion, to abbreviate it. Now, to expand this, there's many ways that we can expand this bracket. Sometimes it might have quite a large power here, so you'll need to use the binomial expansion. Now I'm going to use the binomial expansion for this one, and I could use the combinations method, or I could use Pascal's triangle. In fact, I'll use Pascal's triangle. So if we use Pascal's triangle, it starts with a 1, and then it goes 1, 1, and 1, 2, 1, 1, 3, 3, 1, and finally the one that we're interested in, 1, 4, 6, 4, 1. I'm assuming that you're familiar with Pascal's triangle. These are the coefficients of our terms in cosine and sine. So we start with 1. We've got 1 times c to the power 4. If you're doing the combinations method, this would have been 4c 0, okay? 4c0 would have given us the 1. And then we go plus, and then we put our coefficient down, 4. Combinations method, it would have been 4c1, that would have given us this. Drop the power of c now from a 4 by 1 to 3. And start to increase the power on is, okay? It's is now to the power 1. Next term would be plus, and then we get 6, or in combinations it would have been 4c2, okay? 4c2 would have given you the 6. Drop the power of c to the power 2, and then increase the is to the power 2. And then for the 4 is the next one, 4. Drop power c by 1, so it's c to the power 1, and then increase is up to the power 3. And the last term would be a 1, and I can leave that off. It would be 1 times c to the power 0, which is still 1, and then is to the power 4. Okay? So that's the binomial expansion of c plus is all to the power 4. All we need to do now is just tidy this up. Let's group together the real parts, okay, and then the imaginary parts. Now c to the 4, that's going to be real. We're going to have an imaginary value here. This term here is going to be real because I can see that we've got I squared s squared. Now I squared is going to be -1, so we're going to have minus then 6c squared s squared. This term here, we're going to have I cubed. That comes out at minus I, so that's imaginary, okay? This term here will be real because we've got I to the power 4, which is going to be 1. So we've got just s to the power 4, so plus s to the power 4. So that's the real part. Now we've got to look at the imaginary part, so we'll have I there, and we'll pull that out as a common factor. So this was an imaginary term. It's going to be 4c cubed times is. Okay, well, we got the I out the front, so it's just 4c cubed s. And then we've got an imaginary term here. We've got I cubed, so that's going to be minus I times s cubed. So we've got minus 4c s cubed. Okay, so minus 4c s cubed. Okay, so that's the imaginary part there. Now it does say express cos 4 theta in terms of cos theta. So I can see that I'm going to be comparing this part, the real part, cos 4 theta, and I can see at the moment that it's cos to the power 4 of theta minus 6 cos squared theta sine squared theta plus sine to the power 4 of theta. But if I'm to get it in terms of cos theta, then I can use the identity that sine squared theta plus cos squared theta is 1, which when rearranged, sine squared is 1 minus cos squared of an angle. So what we've got here then is c to the 4. For this second term we've got minus 6c squared, but instead of s squared we can write that as 1 minus cos squared. We'll just abbreviate that to 1 minus c squared. And sine to the power 4, well, that's sine squared all squared, and sine squared is 1 minus cos squared, so we've got plus 1 minus c squared all squared. And then we've got our imaginary term there, so don't have to worry about that one, so we'll just put it in as c cubed s minus 4c s cubed. Okay, let's just expand these brackets now. Okay, so we've got c to the power 4. If we expand this bracket, we've got minus 6c squared and then plus 6c to the power 4. Now for this bracket, 1 minus c squared all squared, that's going to be 1 squared, which is 1. We're going to have minus c squared minus another c squared, so it's minus 2c squared, and then minus c squared all squared, that's plus c to the power 4. And then we've got our imaginary part there, so we'll just write that back in as I times 4c cubed s minus 4c s cubed. Okay, so let's just group this up now. What have we got? We've got c to the power 4, 6c to the power 4, and c to the power 4 there. So that's a total of 8c to the power 4. And then we've got minus 6c squared minus 2c squared, so that's minus 8c squared. And then we've just got the constant there, plus 1. And for the imaginary part, it's just, again, I times 4c cubed s minus 4c s cubed. Now, I did say earlier then that what we were going to do is just compare the real parts. So cos 4 theta is the real part here. So if we compare the real parts, let's just put it down here, compare the real parts, what we've got then is that cos 4 theta is identical to the real part here, which is 8 cos to the power 4 of theta minus 8 cos squared theta plus 1. Okay, well, we've now been able to express cos 4 theta in terms of cos theta. But it's well worth noting at this point, okay, that we could have been asked to expand sine 4 theta in terms of cos theta and sine theta. And if that were the case, we would just compare the imaginary parts. And if we compare the imaginary parts, we would have sine of 4 theta is identical to, and we just take the imaginary part here, and it would be 4 cos cubed theta sine theta, and then we'd have minus 4 cos theta and then sine cube theta. Okay? Now you'll notice that with something like this is about as far as we can take it. We can't really express this nicely in terms of sine theta because we've got cos cubed theta rather than say cos squared theta, which if we did have cos squared theta we could have gone on and written that as say 1 minus sine squared theta and then expanded the brackets. If we'd had say cos to the power 4 theta, we could have thought of that as cos squared theta all squared. In other words, 1 minus sine squared theta all squared, and then gone on to expand the bracket. But as you can see, it kind of stops here. So we've got sine 4 theta expressed in terms of cosines and sine thetas. Okay, so this though is fundamentally the method that we do follow in questions like this, where we've got to express either the cosine or the sine of a multiple angle in terms of cos theta or sine theta. We look at using Demoivres' theorem, expanding the resulting bracket that we have up here, and then comparing either the real parts or the imaginary parts, dependent on what the question expects. So I hope that's given you some idea then on this type of problem.